All right, so now we're incorporating those relational predicates into our proof system, and we're going to use the same rules, UG, UI, EG, EI, plus all the other replacement rules and implication rules we had, but now we just have to be more careful about when we instantiate variables, when we instantiate constants, because we have more than one quantifier on some statements. So we have to be careful with how we're doing this. This is the argument I gave earlier. So Bill's older than Puma, Puma is older than Gaia. If it is true of anything that if one is older than the second is older than the third, then the first is older than the third. So it follows that Bill is older than Gaia. So if Bill is older than Puma, Puma is older than Gaia, the transitive relationship here in 3, and then the conclusion, Bill is older than Gaia. So let's work through this. So 4. So we can't do anything with 1, we can't do anything with 2 yet. I mean, we can combine them if we wanted, which we're going to end up having to do eventually. So yeah, let me just do that right now because we're going to need that. And OPG, and that's 1, 2 conjunction. And why are we going to need that? Because it's going to end up being our modus ponens, right? Because we need this in order to get this. But you might not have seen that right away, but you can always do that later on in the proof. So now, the only thing we can really work with is premise 3. So right now, this universal, this X, is our first universal. So it is the main operator of the statement. So that's the first one we're going to work with. We're using UI, so we're dropping that. So you got to do one quantifier at a time. So we drop that X. Now we have to be careful and make sure that every instance of X in our statement is replaced by the constant or variable that we want to use. And in this case, we want to use B first for X because we have OBG, OPG. So we're going to want OBG, OPG. And I did this wrong. Yeah, this is supposed to be a P. 1, OPG 2. So yeah, we want OBP, we want OPG. So I want my X's here to be B because that's what my conclusion is. So we have OBY and OYZ, then OBZ. And so that's 3 universal instantiation. And I'm going to write a little notation B. So I did B for this first universal instantiation. Okay, and then I'm just going to keep moving along. So I did the X, now I got to do the Y. So I'm going to drop that Y, but I'm going to keep the X. So that's O, B, and which one should I use? P's next, right? I want all my Y's to be P. So O, B, P, and O, P, Z, then O, B, Z. So I haven't gotten rid of the Z yet, so I got to keep the Z there. And that's 5 UI, and I used P for this one. And then I'm going to do my last instance of UI. And again, now the main operator is the Z, and so I don't have any more quantifiers to worry about. So it's O, B, P, and O, P. What should I use? G, the constant I need. And OBG, and that's 6 UI, and I use G in that case. So 3 instances of UI, and I went in the order of operations, the order of the quantifiers that I had. Okay, now that's it, right? So I already did this conjunction of these 2 first premises, and I might have ended up having to do that later on if you didn't see that right away. But because I have that, that is my antecedent. So I conclude OBG, and that is for 7 modus ponens, and that's my conclusion. So what's important here is taking one quantifier at a time, working your way left to right, and yeah, don't skip steps. If you can't use UI and instantiate every single quantifier you have, you have to do 3 instances of UI and work one quantifier at a time. With these multiple quantifiers, you do have one new restriction on UG, which is that you cannot use UG if the instantiated variable is free in any line that was obtained by EI. So check this invalid argument out. So we have for all X, EX, BY. I think he messed up here, the guy in the book, the author, because that y is free even in this first statement. So you use UI on one, which is okay. It doesn't matter if that y is free because you can use UI. There's the x there. And he instantiates an x for the variable. Then he uses EI on 2, but 2 is an EXY. And then he's replacing it. So I think he made a typo here. I almost have been like tempted to email him, but I know he has different versions of this book, and I choose this version of the book because of that free copy that you can find online if you Google hard enough. But I think he made a mistake here. I think it should have been there exists a y such that BXY, not there exists an x such as B. So I think this is a mistake, his existential quantifier here. But the point still remains. Like, so let's pretend that this is E, there exists a Y such that BXY, and then he instantiates A here. So then on 4, he does universal generalization on the X and gets, therefore all X, BXA. But the problem here is that he applied a universal generalization on a line that has a free variable attained by EI. And the free variable is actually attained by UI up here, but he ends up using EI to get that A, which he needed in order to get this universal or this existential generalization later on. So the biggest point here is that you just cannot use UG if the instantiated variable is free on any line that was obtained by EI, and we have an EI here with the free variable X. And so that was the problem. He could have maybe done BAA, but then he wouldn't have been able to use UG, because UG has to be applied to variable. So yeah, this is just invalid, because even if he wanted to use, and he couldn't use like a variable instead of A, because he's using universal existential instantiation, and those only apply to constants. So yeah, this is invalid. He cannot have made this move on UG. But I think this example is not the best because of this confusion between there exists an X. This Y in this first statement is free to begin with. So I don't know if he did that on purpose or not. And yeah, I've been tempted to email him because it doesn't make sense why he would do there exists an X, B, X, Y. Okay, but check out this example. But when he uses EI on 1 to get rid of there exists an X and to get rid of the X's in his statement, he has a variable in there, Y still, but Y is bound. So he uses EI appropriately. He uses it with a constant. He uses it with a constant that's not currently in play. And when he does it, there are no free variables in this statement because the variables that remain are still bound by that universal statement. So then he uses UI a couple of times. And in each case, he uses it appropriately because UI, again, is a very flexible rule. So then he gets this nice conditional, and he gets to use some of his points to get what he needs. And so now he's using UG down here on line 7 or on line 8. He uses UG to get for all Y, B, C, Y. He used EI, which he's allowed to. But the main point here is when he used EI, he did not create a statement with free variables. He created a statement with variables, and the variables were all bound. So later when he uses UG on 7 to get 8, it's valid. It's perfectly acceptable because all these statements can trace back to this EI statement, and this EI statement has bound variables. So in this case, this is a valid instance of using the rule, whereas this case, this is invalid because when he used EI, in this case, he created a statement with a free variable. When he used EI in this statement, he created a statement with a bound variable. So acceptable here, unacceptable here. Okay, so why is this a restriction? So for all X, there exists a Y such that BXBY is translated as every B has a Y that stands in this B relationship with it. But it's not saying that the Y here is the same for every X. It could be a different Y standing in this relation. So here's the example I want to give. Every dog is owned by someone. That's saying that for every single dog that exists in the world, the dogs are owned by someone. but they're not saying that that someone is the exact same person for each dog. Like, in fact, most dogs have a different owner. It's saying that for all the dogs, they all have an owner, but it's not saying that every owner is the same owner. It's not one person owns every single dog in existence. It's saying that every single dog in existence has an owner, and it could be different owners, it could be the same owner, but to make the inference that it's the same owner is invalid because it often case isn't the same owner. So that's the main point for this restriction, which is why you can't have that free variable just floating around, because then it's assuming that it could be the same owner or the same individual in that relational predicate placeholder. So we also have this restriction on UI. So when you use UI, you can create a free variable or free constant. So we have the statement for all x, fx, and gx, and we use UI. Now we have a statement with free variables. So x is free in the statement, and that's okay. We've been working with statements like that, and that's totally fine. But now that we have this relational predicate where we have two placeholders, you have to be really careful about accidentally creating statements that don't have a free variable. So we have for all x, there exists a y such that x, g, y. If you use UI and you use y, which you can use y, right? With UI, you can use any constant, any variable you want. But when you use UI and you use y, you end up creating, there exists a y such that y, g, y. So now the statement is saying that something is in this G relation with itself, and that's not valid. So you can still use UI on statements like this, but you need to use a different variable. You can do this, you can do that, you can do that. When you use a Y in this case, you end up creating not a free variable, but that Y immediately gets bound to this E, this existence claim, and this should be a backwards E. This isn't really a restriction on UI, but it's more just a be careful what variable or what constant you end up using, because you don't want to accidentally use a variable that's already bound by some other quantifier in the statement. You want to use a variable that's not bound by any quantifier. Like in this case, you create that free x, which is what we want, because it's still saying that there's an x in this G relation to y. We use a y variable, you end up saying there's a y in G relation to itself, and you don't want to do that. Okay. And then one last suggestion or advice with these relational predicates is being careful with CQ, the change of quantifier rule, replacement rule. So you want to go step by step and not skip over quantifiers when you use CQ. So let's say we have the statement, it's not the case there exists an x, and for all y, x, g, y. You want to use change a quantifier, you have to go one quantifier at a time. So you push the negation through one quantifier, this first one, so that particular changes to a universal. That negation stays in that space that it's pushed through, and then the universal stays the same. And then you have to use another instance of CQ in order to push it through that second quantifier, change that universal to a particular, and then get that negation on the predicate rather than on the quantifier. So you can't use CQ once and push it through two quantifiers. You can only use CQ for one quantifier. And then you can't push it through both and only change one quantifier. You would have to change both quantifiers. And then conditional proof, indirect proof, exact same as before, with the same restriction of not using UG when the first is step. That first assumption has an unbound or a free variable, but other than that, there are no additional restrictions for conditional and indirect proof with using these relational predicates. Okay, so now we just have identity left, and then that's it.